Assalamualaikum warahmatullahi wabarakatuh and good day everyone. All right, so now we are going to focus on our next chapter, which is chapter 5 here, partial differential equation. Okay, so in chapter 1, chapter 2, chapter 3, we have discussed about ordinary differential equation, but now we are going to focus on partial differential equation. Okay, so remember in chapter 1, we have done with first order differential equation. Now we have a second chapter, second order differential equation, and then the third chapter, how can we solve those differential equation by using Laplace, right? And then we have Fourier series, where that Fourier series is going to be used in here, chapter 5, where we are going to use, where we are going to find the solution for partial differential equation. Okay, so what is partial differential equation? All right, now let's take a look at the basic definition and terminologies here. Okay, we are going to have method of separation of variables. We are going to solve by using the Lambda method. Okay, so for this case, for this chapter, we are going to have two methods, method of separation of variables and also the Lambda method. All right, we're going to discuss about three types of partial differential equation, which is heat equation, wave equation, and Laplace equation. All right, now let's take a look at the basic definition and terminologies. All right, so partial differential equation. Now, let's say you have a function of u, where those function of u is in terms of x and y, where x and y are the independent variables. So we have more than one independent variables. So a PDE, a partial differential equation, is an equation containing at least one partial derivative of u, where u is a function of x and y. So we can find the partial derivative of u in terms of ux, uy, uxx, uyxy, and also uyy, where ux is for derivative of del u del x, and then uy del u del y, u double x del square u del x squared, u double y del square u del y squared, and uxy is equals to uyx, where this one is derivative of y to del u del x, and then uyx is derivative of x to del u del y. All right. Okay, now there are various types of partial differential equation. So for this one, we have wave equation. Okay, we have heat equation, one-dimensional of wave. As you can see, you have one-dimensional of wave consists of u, x, and t. Right, now two-dimensional of wave consists of u, x, y, and t. Okay, one-dimensional of heat consists of u, x, and t also. Okay, all right. As you can see, the difference between one-dimensional of wave and heat is where wave have del squared u del t squared. Heat only have del u del t. Okay, then we have two-dimensional of Laplace. We have u, x, and y. Then we have three-dimensional of heat. Okay, where we have u, x, y, and z, and also t. Okay, so we are going to learn, we are going to use about this partial differential equation here for this topic. Okay, and now how can we solve this? All right, so we are going to have method of separation of variables, right? So remember, what is partial differential equation? Let's say we have a function of u in terms of x and y, then a PDE is an equation containing at least one partial derivative of u, ux, uy, u double x, u double y, and so on. Okay, so these are the example of partial differential equation. We have wave, we have heat, we have Laplace. Either it is one-dimensional, two-dimensional, or three-dimensional. All right, so now, how can we find the solution of this? So we are going to have method of separation of variables, or we call it as a MSV. Okay, and also the lambda method here. Okay, but this for the lambda method is only for wave for infinite length. All right, now let's take a look at one by one here. What is MSV? Okay, so now let's discuss about the MSV method. Okay, so in PDE, we are going to use this MSV to find the solution. All right, now what is MSV? Okay, MSV is a method of separation of variables. Right, so let's discuss. Let's consider the heat equation for one dimensional. Okay, as you can see, for heat equation of one dimensional, we have del U del T equals to K squared del squared U del X squared. Okay, so now when you have del U and del X and del T here, we need to find or we need to know, our aim is to find the solution. Okay, this is your differential equation. Of course, we want to find the solution. So as you can see, it consists of del U, del T, and del X. So the solution should be a function of U in terms of X and T. Okay, where a function of U is a function that depends on X and T. Okay, so when this is your differential equation, okay, this is your PDE, right? Then you should know that the solution should consist of should consist of U in terms of X and T. Okay, because U depends on X and T. Okay, now the basic idea of MSV is to seek a solution. So now, of course, this is your function. U is in terms of X and T. So let's assume the function here consists of a function of X and a function of T. Okay? All right, the function of U here consists of the function of X and the function of T, where X is some function of X and T is some function of T. So this is just an assumption. Okay, now, by separating the variables X and T, we reduce the problem of solving the PDE to solving the two ODEs. Okay, so from here, you know that in the heat equation given, it involves derivative of U with respect to T once and derivative of U with respect to S twice. So what you need to have is U T and U double X. That's why here U T and U double X, because considering the problem of this, okay, of this one-dimensional heat equation. Okay, we involve del U del T and del squared U del X squared. So we assume that the solution should be in terms U in terms of X and T, where U function is in terms of X and T. So we just assume that it is a combination of function X and T. So from here, in order to match with here, so you need to have UT and also U double X. Okay, where for UT, you just differentiate T once. And for U double X, you just differentiate X twice. Okay, so now, as you can see here, therefore equation 1 becomes, where is equation 1? The original problem. So now, from here, we substitute to the heat equation, where heat equation involves del U del T. So this is your del U del T. Now, X T prime T equals to k squared, del squared u del x squared. So this is your del squared u del x squared. X double x and t. Okay. So now from here, as you can see, it becomes like this. So x t prime equals to k square x double prime t. Then we rearrange. We put x together and t together. So x double prime over x equals to 1 over k squared t prime over t. Okay, since a function of t can equal to a function of x only when both functions are constant, right? Then this function can be equal to this function, okay, only when both functions are constant. So we create this two equation equals to another constant, let's say lambda. So now we have x double prime over x equals to lambda. 1 over k squared t prime t equals to lambda. So from here, we can have this and this, okay? X double prime minus lambda x equals to 0. T prime minus k squared lambda t equals to 0. Okay, so from here, from this one-dimensional fifth equation, del u del t now equals to k squared del squared u del x squared now can be reduced to this. Okay, so our purpose is to find a solution based on this. Right, so this is how MSV works. So thus, the problem of solving PDE now is reduced to solve the two ODEs. Okay, so instead of solving the PDE directly, now it is reduced to ODE, to two functions here, two equations here. So it will be easy for you to find the solution. Okay, so the above steps are basic steps in the method of separation of variables. Once the variables are separated, solution process will be proceeded by applying the boundary condition and initial condition. So now let's try to reduce other PDEs here. Okay, we have wave equation. Okay, we have wave equation here, where wave equation here consists of del squared u del t squared alpha squared del squared u del x squared. So you know that you assume that the solution should consist of u, x, and t, where it is a function of x and t. And you have to have del squared u del t squared, where it is u double t, where it can be xt double prime. And you should have del squared u del x squared, so you should have u double x, means that you should have x double prime t. And then you substitute to the given equation, substitute to PDE given, where now del squared u del t squared is u double t is xt double prime equals to alpha squared x double prime t. And these two equations are equal when both are equal into another constant. So we have xt double prime equals to constant, sorry. Before that, we need to rearrange, sorry. Okay, so we have to rearrange according to the variable. So we put x together, okay, and then we have 1 over alpha squared t double prime over t. So now these two equation is equal when we have another constant of lambda here. So we equal the two equations here with another constant of lambda. So we can put x double prime over x equals to lambda and t double prime over alpha squared t equals to lambda. So from here we are going to have two equations. So it can be x double prime minus lambda x equals to 0. Okay. And we have T double prime minus lambda alpha squared T equals to 0. So now instead of del squared U del T squared here, okay, instead of del squared U del T squared equals to alpha squared del squared U del X squared, here now it is reduced to these ODEs. Okay, so this is how MSV works. So we just reduce. After this, we're going to take a look how we can find the solution. All right, so let's try another one, Laplace. Okay, now Laplace here consists of del squared U del X squared, del squared U del Y squared. Okay, so you know that the solution should consist of U, X, and Y, where it is a function of X and Y. Okay, and from here you should have del squared U del X squared, so you should have U double X. So this is actually same. Okay, where you differentiate X double prime here. And then we have del squared U del Y squared, where it is U double Y. Okay, so X Y double prime. And then substitute to the PDE. So we have here X double prime Y plus XY double prime equals to 0. Okay, so we rearrange. All right, so we rearrange. We have X double Y equals to negative XY double prime. All right, and then rearrange. We have X double prime over X equals to negative Y double prime over Y. All right, where for this case, we need to equal these two equations to another constant so that they are equal. Then we can separate these two. Okay, then we can have two equations of ODE. All right, this is how we reduce. Okay, this is the phase when where we reduce from the partial differential equation to ordinary differential equation. Now we have two equations of ODE here that we need to solve. Okay. So instead of this, now we are going to find the solution of this. Okay, just like the example given here. All right. Okay. So now let's try to find the solution. Okay. Okay, we start with heat first, right? Solving heat equation by using MSV. So this is heat equation for one-dimensional, okay? The given initial condition, right? And there are three types of boundary condition, okay, where the first type is for zero endpoints, where we just have U and U, meaning that we substitute X with 0 equals to 0, and we substitute X with N also equals to 0. So 0 endpoints. Okay. And then for insulated endpoints, we have UX, where we differentiate U with respect to X, and then we substitute we substitute T with 0 will equals to 0, and we substitute X with L equals to 0. So L is certain value. And mixed endpoint is a mixture of U and also UX. Okay. So now let's discuss this example. Okay. So now this is what we call heat equation for one-dimensional. We are going to find the solution by using MSV. Okay. Remember, In order to solve, by using MSV, we always need to reduce to ODE. So this is PDE. So first we have to reduce to ODE. Okay, so our first step is to reduce to ODE. Okay, where, as you can see, this heat equation, we have U, okay, we have U, we have X, and we have T. So we assume that the solution should be U, X, T is in terms of X function and T function. Okay, and it involves del U del T, so you need to have U T and del squared U del X squared. So you have to have U double X, where U T X T prime, U double X X double prime T. And then substitute to the PDE, where del U del T is U T is S T prime, equals to 4 X double prime T. So now we rearrange. X double prime over X equals to T prime over 4T equals to another constant of lambda, so that we can reduce to 2 ODEs of X double prime minus lambda X equals to 0 and T prime minus 4 lambda T equals to 0. So we have 2 ODEs here. Okay, next we need to form, next step, because this is your first step, reducing PDE to ODE. Next step, we have to have the condition. Okay, so now you have U0T equals to 0, U1T equals to 0. Okay, second, form the boundary condition of the ODE. This is the condition from this PDE. Now we have ODE, so we need to have the boundary condition for ODE. So given U0T, and you know that UXT equals to XTT, so U0T means X0 TT, okay, equals to 0, equals to 0. X0 is what? Okay, X0 is unknown and T cannot be 0. Okay, so X0 equals to 0. So from here, X0 equals to 0. So this is the first condition. Then the second one, we have U1T, and you know that U1T here comes from UXT, where XXTT. So here X is 1, then X1 TT equals to 0. Then X1 equals to 0. So these are the boundary condition. Okay, now what we're going to do from here is to consider all cases of lambda. So we have X double prime minus lambda X equals to 0, T prime minus 4 lambda T equals to 0. So our next step is to consider all cases for lambda. Okay, so first step, reduce PDE to ODE. Okay, second step, forming the boundary condition of ODE that you obtain, because the condition given is for PDE. So the condition given is for PDE. Now we have boundary condition for ODE because we have reduced this PDE to ODE. So now we need to consider all cases for lambda. Okay, and you know that the cases for lambda here is applied to X double prime minus lambda X equals to 0, T prime minus 4 lambda T equals to 0. So the first case that we need to consider is when lambda equals to 0. Okay. where when lambda equals to 0, when lambda equals to 0, we have x double prime equals to 0 from here. Okay, solving first x and then followed by t. Okay, now when x double prime equals to 0, you know that from the characteristic equation m squared equals to 0. So m1 equals to 0, m2 equals to 0. By homogeneous equation from chapter 2, we will have x solution is a plus bx. Okay, where this is real and equal. E mx a plus bx. So your m is 0, then only left with a plus bx. Okay, now we have the solution of x. X equals to a plus bx. So apply the condition x0 equals to 0. When x0 equals to 0, then a equals to 0. Okay, when x1 equals to 0, so a0, then b equals to 0. We'll give you a and b equals to 0 here. We'll give you x equals to 0 plus 0. X is 0. So we are assuming that uxt is the solution of uxt here is in terms of function x and t, right? So now x is 0, then no point to find t. Okay, now when x is 0, you substitute here, you will get uxt equals to 0, where we put no interest in such solution. Okay, then we consider another case. Second case, case 2, where lambda greater than 0. Okay, let's say lambda equals to b squared. Okay, now when lambda greater than 0, again, we are going to use the same ODE, x double prime minus lambda minus p squared x equals to 0, p prime minus 4p squared t equals to 0. So let's start with x first. Okay. So here we are going to have the characteristic equation of m squared minus p squared equals to 0, m equals to p. Okay, plus minus p. All right, where for this case, you can have the solution of x equals to aepx plus be minus bx. Okay, apply the condition. X0 equals to a plus b equals to 0. Okay, from here b equals to negative a. And then we have another condition, x1 equals to a e p plus be minus p equals to 0 and b equals to negative a. So aep minus ae minus p equals to 0. All right. So here we have aep minus e minus p equals to 0 and a equals to 0. So when a equals to 0, b also equals to 0. So x equals to 0. Then again, we have to know that our assumption of solution should be in terms of uxt, x times t. Now, x is 0. Now we will have uxt equals to 0. Then we put no interest in such solution. All right, so when you got x equals to 0 for you, then no point to find t because you will have 0. Okay. Okay. Next, we need to consider another case, okay, where we have to consider all cases for lambda equals to 0, greater than 0, and another case is case 3, lambda less than 0. So let's say lambda equals to negative p squared. Okay, again, x double prime minus p squared x equals to 0. And we are going to have t prime minus 4 minus p squared t equals to 0. So let's proceed with x first. So we have here x double prime plus p squared x equals to 0, right? Where we are going to have a characteristic equation of m squared plus p squared equals to 0, m equals to negative plus minus pi. Then your solution of x should be a cos px plus b sine px. All right. Okay, now apply the condition. X0 equals to 0. A cos 0 plus b sine 0 equals to 0. So we have here a equals to 0. Okay. And then we have another one, x1. A cos p plus b sine p equals to 0. And you know that a is 0, so b sine p equals to 0. Okay. And from here, b cannot be 0. So sine p equals to 0, where sine and pi also equals to 0, then we can have p equals to n pi, right? So when p equals to n pi, then your x should be b sine n pi x. Okay? We cannot solve for b here, then we just have a constant b there. Okay, then now we have a function of x, then we can have a function of t because u is in terms of x and t. So from the second equation, we have t prime plus 4p squared t equals to 0. By characteristic equation, you have m plus 4p squared equals to 0 will give you m equals to negative 4p squared. And from here, you know that your t is equals to CE negative 4p squared t. This comes from the solution for real and distinct for homogeneous equation. Okay. And since p equals to n pi, so Tn should be c exponent negative 4 n pi squared t. Okay. So from here, you know that the solution of uxt equals to a function of x and a function of t, right? Because we have done the first assumption here. And now your u and xt now is x and x, t and t. Why we have n here? Because we have this n pi, where n equals to 1, 2, 3, and so on. So now your u and xt equals to xn is bn sine n pi x, and t is ce negative 4 n pi squared t. Okay, so we have here bn times cn. Let's bn times cn equals to bn. So bn sine n pi x exponent negative 4 n squared pi squared t. Okay, so this is the solution from case 3. And then what we are going to do is we want to find the solution of, okay, our next step, we have done with the first step, second step, and third step. Okay, our next step is to sum all cases of lambda. Okay, so uxt is comes from u case 1 plus u case 2 plus u case 3. So this is the summation of this one is 0, this one is 0. So u case 3 is the summation from n equals to infinity of bn exponent negative 4n squared pi squared t sine n pi x. Okay, now this is the general solution of uxt. Okay, and remember we have the condition. We have the boundary condition given. All right. Sorry, the initial condition given. Ux0 equals to x over 4. Okay. Then we can find the value of constant there. So apply the next step, apply the condition. So we have applied the first and second condition here, right? Now we are going to use this ux0 equals to x over 4. Okay, so now ux0 equals to x over 4. Okay, and we have uxt is the summation of bn exponent minus 4n squared pi squared t sine n pi x. So we have here, just substitute t equals to 0. So ux0 equals to summation of n equals to 1 to infinity bn, t is 0. So the exponent to the power of 0 sine n pi x. Okay, equals to x over 4. Right? And remember, from Fourier series, fx equals to summation n equals to 1 to infinity of bn sine n pi x over L. And matching to this, as you can see, fx equals to x over 4. Bn equals to Bn. Right. Sine n pi x equals to sine n pi x over L. And as you can see, L here is 1. So we can find this Bn actually by matching this with Fourier series. And you know that Bn from Fourier series equals to 2 over L, integrate from 0 to L, fx sine n pi x over L dx. So substitute everything. L is 1. Okay, fx is x over 4 sine n pi x over 1 dx. So solving this will give you the value of Bn. Okay, to solve this will give you the value of Bn 1 over 2n pi times minus 1 to the power of n plus 1. Now this is your Bn, so your final solution should be uxt equals to summation of n from 1 to infinity. Remember, initially this is your u. Now we have your Bn. Then just substitute your Bn, where Bn is equals to minus 1 to the power of n plus 1 over 2n pi exponent minus 4n squared pi squared t sine n pi x. So this is how you find the solution for partial differential equation. It's quite long and you have to be very careful with your calculation. All right. So I'm going to give you only one example for this video. Okay, after this, let's discuss the rest of the example in our class. All right. So thank you guys. Assalamualaikum.